Hello there, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I am Dr. Owusu. In today's session, we are going to be continuing with our series on practical chemistry and specifically looking at acid-base titrations. And so over the course of the next hour or so, I will be giving you all the tips and tricks that you need to carry out titration successfully and to obtain accurate results. As usual, I will encourage you to use the chat boxes to ask if there are any questions, and I will be pausing at appropriate points to answer those questions for you. Towards the end of the session, we will also look at some practice exam questions and a couple of titration calculations so that we take a rounded look on the topic. Okay, so before we start, I will connect my tablet and then we will be ready to roll. Okay, so on your screens, you should see a title page, Practical Chemistry and Acid-Based Titrations. Of course, to start with, I would assume that you all know what a titration is, given that you will have first encountered it at GCSE. Okay, so in a titration, you've got a solution whose concentration is known very accurately, and that solution is then going to be used to find the concentration of a second solution. Okay, so that second solution whose concentration we don't know is often referred to as the analyte. You don't need to call it that. So we're going to be analyzing it. And we're going to be analyzing it using a different solution whose concentration we know very accurately. Okay, so to start with, we need to have a solution whose concentration we know very accurately. And this is what is referred to as a standard. Okay, so we need a standard solution. And as part of the A-level course, you will have been taught to prepare a standard solution that you would then go on to use in a titration. So we're going to look at that first before we look at the actual titration. Okay, so what do we need to make a standard solution? So on your screen, you should see an assortment of apparatus that you need to prepare your standard solution. Of course, we will make reference to all of these pictures of different pieces of apparatus, which I hope you can all recognize. I can't assume too much these days. But the first thing we need to do is to calculate the mass of the solid that we're going to be using to prepare our standard solution. Okay, so standard solutions are often prepared from a solid that is dissolved in or soluble in water. Okay, so I'm going to highlight some of the key points about making the standard solution as we go on. So we need to calculate the mass of solid needed. Why do we need to calculate the mass of solid needed? Because we are hoping to make a standard solution of known concentration. If you're going to make something of whose concentration is known, then you do need to know its mass accurately and measure its mass accurately, and then dissolve it in the correct volume of water. Okay, so for a standard solution, we need to be able to measure the mass of our solid. Now, the solid itself is often chosen to have a high molecular weight or high molecular mass, so that you reduce or minimize the percentage error in the measurement of mass. Okay, so okay, so we need a standard that is obtained from a solid that has a high molecular weight or high molecular mass or high MR. Okay, so once you've chosen a suitable standard, you then need to dissolve it in water. So that solid must be soluble. Okay, so must be readily soluble in water, and it must also be very stable. It shouldn't decompose over time, so that you've got a different substance dissolved in your solution than what you started with. Okay, so it must be stable. Okay, so once we've decided on our solid, we need to now measure its mass accurately. We've done the calculation to work out what mass will allow us to get the correct concentration. Now we need to weigh the mass of our solid. And the second step on your screen says to weigh the mass by subtraction. Now this is very important. It's the first tip for you to get accurate results in any titration is measuring masses accurately when preparing a standard solution. Now, what you need to do is tare the balance or zero the balance. Place your weighing boat on that balance. There's a weighing boat. Place your weighing boat on the balance, and then using a spatula to add your solid to that weighing boat, so that what you end up with is a mass of your solid and weighing boat together. Okay, so let's say you want to transfer or dissolve 5 grams of your solid in your standard solution. Weighing boat placed on the balance, and then on top of the mass of that weighing boat, you're going to add approximately 5 grams to that weighing boat. Okay, so once you've done that, you then need to transfer your solid that you've just weighed into a beaker. Okay, so you're going to pour the solid into the beaker, and it is very important once you've done that, you re-weigh the empty weighing boat so that we know exactly how much of that solid has ended up in the beaker. Okay, so weigh by subtraction. This is very important because we need to know exactly what mass we're going to dissolve in our water to make the standard solution. Okay, so once you've done that, once you've transferred your solid into your beaker and then reweighed your weighing boat and got the mass by subtraction, you then need to dissolve that solid in distilled water. You can't use ordinary water, which will have other solutes dissolved in it, and that might potentially affect a titration you go on to do. We need to ensure that it is water and nothing else. So distilled water has to be used, or deionized water. Okay, so you're going to dissolve your solid in your distilled water, but you're not going to add the maximum volume of water required immediately. You need to dissolve it in a volume of water that is significantly less than what the total volume is going to be. Okay, so and the reason being that if you find that your solid isn't as soluble in water as you thought, then it's going to require more than the maximum volume that you thought would be required to make your standard solution, and that therefore changes the concentration. So you want to make sure that we're going to be using the exact maximum volume that we've calculated for our to obtain the correct concentration for our standard. So if you're making a standard solution that has a total volume of about of exactly 500 centimeters cubed, then you want to make sure that you're initially dissolving your solid in, say, 200 centimeters cubed, and then you're going to rinse the beaker with some more distilled water to ensure that all the solute is being dissolved in water and being transferred to our volumetric flask. Okay, so you're going to add about 200 centimeters cubed of water if we're making a 500 centimeter cubed standard solution. Okay, so what you're going to do next, having dissolved your solid in about 200 centimeters cubed of distilled water, is to transfer it via a funnel into our volumetric flask. So we've got a volumetric flask here, got a plastic funnel, and we've just dissolved our solid in this beaker using 200 centimeters cubed of water. Okay, so we've got that to about sort of there. And then what you're going to do is transfer the solution which you've made and stirred with a glass rod into our volumetric flask. And so you're going to have a volumetric flask that is only partly up to the volume we require. Okay, so once you've done that, you then need to rinse out the empty beaker with some more distilled water to ensure that there's no solute left here. And you can do that in small increments. So you can then add 50 centimeters cubed to the beaker, rinse it out, transfer it via your funnel into your volumetric flask, and do that another couple of times. And then as you approach the mark, you can see there is a mark there indicating where 500 centimeters cubed is. As you approach the mark at this stage, I would stop transferring directly from the beaker via the funnel and instead use my plastic pipette to slowly add dropwise water to the mark. Okay, so if we were to zoom in on, I use a pen to show that, if we were to zoom in on the mark, let's say that is the mark, you want your water to be, or the solution to, the meniscus of your solution to be sitting on the mark. Okay, so you want to make sure that you've got the exact volume required, and the way to do that is to add your water sort of drop by drop as you approach the mark. Now, once you've done that, and only when you've got your solution up to the mark, do you stop at your flask and then invert it several times to make sure that everything is dissolved and mixed in properly. Okay, so that is how you would go about making your standard solution. The key points here are weighing the mass accurately. How do you weigh the mass accurately? By subtraction, dissolving initially in a smaller volume of water, distilled water, than you require to make the standard solution, making sure you stir it with a glass rod so that it's all dissolved, and then transferring it into your volumetric flask via a funnel, and then making sure you wash or rinse your beaker with some more distilled water. And as you approach the mark, so about perhaps a centimetre height from the mark, you should then use your plastic pipette to add water, distilled water, dropwise to get it to the mark. Okay, so that's the first part of our practical done. We have prepared an accurate standard solution containing a known number of moles of our solid in a known and very accurately measured volume of solvent, water. Okay, so we're now ready to use this standard solution in a titration. Now, at this point, I'm going to very quickly check to see if there are any questions on preparing a standard solution. Okay, and currently there are no questions, so what I'll do is carry on to looking at how to use our standard solution in a titration. Okay, so on this page, you can see all the typical pieces of apparatus you're going to need in carrying out a titration. Okay, so let's have a quick look at what some of these are. So obviously we've just discovered, or not just discovered, but certainly looked at the beaker and sort of glass rod and funnels and your distilled water wash bottle. The pipette, so to differentiate it from a plastic or dropper pipette. So there's a glass pipette which measures very accurately one volume. So these glass pipettes come in different volumes. So you might have a small volume as 10 milliliters, so you can have your pipette measuring 10 milliliters very accurately. You can also have a 25 milliliter glass pipette. You can have bigger ones as well. The standard size in any school lab is the 25 milliliter or 25 centimeter cube glass pipette. Okay, so that's your glass pipette, and the way to fill that glass pipette safely is to use a pipette filler, which is that rubber pipette filler shown in the top left corner of that box. Okay, so that's your pipette, and your burette is this much larger piece of glassware which is held in a burette holder and which is attached to a clamp stand. Okay, so the burette can measure a range of volumes from 0 to, well, in this instance, the typical maximum volume for a burette would be 50 centimeters cubed. You can have bigger or smaller burettes. So typically in a school lab, you'd have a 50 centimeter cube burette, and it can measure volumes to an accuracy of 0.05 centimeters cubed, from 0 all the way to 50 centimeters cubed. Okay, so in any titration, generally, though this isn't always true, generally the thing that you're analyzing, the thing that you want to know the concentration of, you're going to pipette into your conical flask. So if we wanted to know the concentration of our sulfuric acid, that's going to go into that conical flask. and you're going to add a suitable indicator. So in this titration, it looks like we're at the end of the titration because the indicator used, phenolphthalein, shows pink in alkaline solution. So you've got sodium hydroxide solution from the burette being added to your acid, and when all of the acid has been neutralized and there's just an excess of your alkali, it goes pink. Okay, so to start any titration, you do need to rinse the pipette and the burette. And the way to do that is to use whatever solution those pieces of glass are going to be measuring. So if the pipette is measuring the sulfuric acid, you need to rinse the pipette with a small amount of sulfuric acid first, and then that ensures that any contaminants are gotten rid of. And if there's no way of changing the concentration of the acid you're going to be putting into the pipette because you've washed it with water instead, which would have a dilutory effect. So rinse your pipette with your whatever you're measuring, whatever solution you're measuring. In this case, it's the sulfuric acid. You're going to rinse your burette with sodium hydroxide because you're going to be filling it with sodium hydroxide. Okay, and once you've done that, you need to make sure that the bit below the tap of your burette is also filled with sodium hydroxide. It is important that you ensure there are no air bubbles at all. If there are, you need to drain your burette and make sure that you get rid of that air bubble. The reason being, if there is an air bubble and you start to add your solution to your conical flask, whatever volume reading you take will not have factored in the fact that you had actually got some air in your burette. And so what you've added is actually less than what you think you have. So it is very important that you get rid of any air bubbles. Okay, so that's a quick introduction to the pieces of apparatus you're going to need in your titration. Let's look at how you're going to carry out the titration. Once you've rinsed your pipette and your burette, the first thing to do is to accurately pipette your solution that you're going to be analyzing, the solution that you want to find the concentration of. You're going to pipette that into a conical flask. So in this case, we've got sulfuric acid. The sulfuric acid is going to be pipetted into the conical flask. You're going to use the pipette filler to allow you to do that safely. You don't want to be sucking on your pipette as if it were a straw. That would be obviously very dangerous to do, given that you're working with a corrosive solution of sulfuric acid. So you're going to pipette accurately into your conical flask. And again, just as we saw with the volumetric flask, the glass pipette will have a mark to which you're going to fill the pipette to, and that is the exact volume indicated on the side of the pipette. So if we're looking at a 25 centimeter cube pipette, that volume is exactly 25 centimeters cubed, and the bottom of the meniscus must sit on that line. Okay, not above it or just below it, it must sit exactly on that line. Now, when you then transfer your pipette into the contents of your pipette into the conical flask, at the very end, you need to touch the tip of the pipette to the solution so that all of the maximum volume has been drained into your flask. Now, there will always be a tiny drop of your solution left in the pipette. This has been accounted for or factored into the total volume, so don't try and force it out. It often leads to a disastrous breakage of your pipette because students are tapping the pipette against the sides of their flask. So that tiny drop at the end of your pipette, don't worry about it. It's been accounted for. You just need to touch the tip of your pipette to the surface of your liquid, and then that's your measurement, the transfer done into your conical flask. And then what you want to do next is to fill your burette with your solution that you're going to be titrating the acid with, in this case, your sodium hydroxide. You can fill it up to the 0 mark, which is up at the top, or you could fill it to just below. It doesn't matter. The important thing is that you note down what the starting volume is. Okay, so the starting volume could be 0.00 centimeters cubed, or it could be 1.20 centimeters cubed. It doesn't matter. What matters most is that you record what this starting volume is, okay? Because the burette works by taking 2 readings, an initial volume and a final volume. And when you subtract the initial from the final volume, you have an accurate measurement of how much solution you've actually added or used in your titration. Okay, so you're going to, the other thing I omitted to mention, of course, is the indicator for your solution in your conical flask. Because this is an acid-based titration, you're going to need an indicator. Most sort of acids and alkali are colorless liquids, and we'll have no, sorry, repeating myself, colorless liquids, which therefore means that to know when the endpoint of the reaction is, you need to have an indicator present. And so in this case, phenolphthalein is used. And because indicators themselves are weak acids, it's important that you only add just a couple of drops, 2 or 3 drops, because too much would affect the titration itself. So that you've got sodium hydroxide neutralizing a significant amount of your weak acid when you want it to be neutralizing your sulfuric acid. Okay, so we've got our indicator ready. We've got our burette filled with our sodium hydroxide. What we're going to do now is to add our sodium hydroxide to the contents of our conical flask. And the first time you do your titration, the first run, it is known as a trial run. So this is just to give you an idea of what volume is going to be needed to neutralize the acid in our conical flask. And so it is okay to overshoot the actual volume needed. Okay, so you need to pay attention to the contents of your conical flask, swirl your conical flask as you're adding the sodium hydroxide, and occasionally do stop and using your wash bottle, so this wash bottle containing distilled water, rinse the insides of your conical flask to make sure that all of the sodium hydroxide being added goes into your acid solution. Okay, so that is very important to improve the accuracy of your titration. Okay, so always stop to rinse the insides of your conical flask. Now, this some students might think would affect the accuracy of the titration in an adverse way. Not at all, because you're not changing the number of moles of acid in your conical flask. And so you're still going to use or require the same volume of sodium hydroxide to neutralize the acid in your conical flask. Okay, all you're doing is ensuring that all of your sodium hydroxide goes into the reaction flask to neutralize the acid. Okay, so once you've got your trial run done, you then need to do accurate runs to get concordant results. Okay, so let's say your trial run suggests or uses 27 centimeters cubed of your sodium hydroxide. In your second run, which is your first accurate run, when you reach about 24 centimeters cubed, it then makes sense to actually slow down the rate of addition of your sodium hydroxide. But you're going to add your sodium hydroxide drop-wise, drop by drop, so that you're very careful not to overshoot the endpoint. Okay, so you want the palest pink possible in this example, where we're adding sodium hydroxide to our sulfuric acid. Okay, so drop-wise addition as you approach that so equivalent volume, so the volume needed to neutralize our acid. You need to do that drop by drop so that you don't overshoot it. Okay, so and then you need to stop addition as soon as the color change is observed, and you need to record the final volume. Okay, so that's how you would go about carrying out this titration. Now, how do we record the results obtained from the titration? You will all be familiar with a table looking like the one I've got on your screen, and then you put in some made up data for us to have a look at. So let's say that our initial volume for this titration is 2 centimeters cubed, or 2.00 centimeters cubed. Okay, remember the burette can measure to an accuracy of 0.05 centimeters cubed, and so your burette readings must be to 2 decimal places and ending in a 0 or a 5. Okay, so 0.05, so it can be 0.00 or it can be 0.05. So we start with our initial volume of 2.00, and let's say we have a final volume of 28.60. Okay, so our trial run has a Titer volume of 26.60. Okay, so we now have an idea of where our what our Titer volume is. So we know that in our first accurate run, we need to slow things down when we reach about 24 centimeters cubed, and then add our sodium hydroxide with swirling of your conical flask, drop by drop, so that we don't overshoot that mark. Okay, so we've got 26.60 for the first run for our trial run. In our first proper run, we fill the burette all the way up to the 0 mark, so 0.00, and then we carry out our titration, and we find that we have used 25.40. Okay, so Titer volume is 25.40, and then we go on to do our second accurate run. The second accurate run, again, we're for convenience starting with a starting volume of 0.00, and when we've carried out our titration, we find that the end volume, the final volume, is 25.30. So we have a Titer volume of 25.30. At this stage, it is important to compare the two accurate Titer volumes. So we've got 25.40 and 25.30. They are within 0.10 of each other, and that means that we've got concordant results. Okay, so concordant results are volumes within Okay, so at this stage, you can stop. There is no need to go on to obtain further Titer volumes. As soon as you have two results that are in agreement, two results that are within 0.10 centimeters cubed, that is your titration done. Okay, and then what you need to do is carry out a calculation to find the mean Titer volume. Okay, so the mean Titer volume can only be calculated using those results that are concordant. Okay, so in the example above, our two results that are concordant are 25.40 and 25.30. And so when you find the mean of that, you should get 25.35. Okay, so so that's your mean Titer volume, and that's the volume that you would go on to use in a calculation to work out the concentration of your unknown. Okay, now where things become tricky for concordant results is if your first two results don't agree. So if we've got, say, 25.40, 25.60, you can say these two volumes are not in agreement because they're not within 0.10 centimeters cubed of each other. Okay, so that means that you need to go on to do a further titration. And then let's say you do your third accurate run, and this time round you get a volume of 25.50. Okay, so we now have three Titer volumes. You have these two being concordant, but you've also got your 25.50 and your 25.40 being concordant. So what we need to do here is to ensure is to use all three values because all three values are in concordance with each other. So 25.50 is concordant with 25.40. It's also concordant with 25.60. So when we find the mean, of course, it's going to be 25.50. Okay, so that's one example where you might need to think a little bit more about how you carry out your mean calculation. Okay, so at this point, I'm going to check to see if there are any questions, and if there are, I will continue with our work. Okay, so no questions, and we've just looked at how to calculate the mean Titer value. And again, before we move on, to point out that all of your volumes must be to 2 decimal places ending in a 0 or a 5, because your burette can measure to 0.05 centimeters cubed, which is the volume of 1 drop of solution from the burette. Okay, so we've got the results of our titration. Now, the titration practical lends itself very well to examiners testing you to see your understanding of uncertainty and calculating percentage uncertainties and percentage errors. Okay, so each instrument that you use will have an inherent uncertainty about the measurement that it can make and how accurately it can make a measurement. So if we take a balance, for instance, if it's a 3 decimal place balance, a 3-figure balance, it can measure accurately to plus or minus 0.001 grams. Okay, so if you measured 25 grams exactly, it would be 25.000 on the apparatus. But the inherent error would be plus or minus 0.001 grams. So it could be 25.001. It could be 24. That's a tricky one. 24.99. Well, yeah, that'd be 24.990, I believe. You correct me on this. So there is this inherent sort of error associated with the balance. So this uncertainty in the reading of that mass. Okay. Similarly, if you use a volumetric flask, there is an error of plus or minus 0.1 centimeter cubed. So your 25 centimeter cubed volumetric, 250 centimeter cubed volumetric flask could be 250.1, or it could be 249.9 centimeters cubed. Okay, so there's that plus or minus 0.1 centimeters cubed. A pipette that measures 25 centimeters cubed has an error of plus or minus 0.1 centimeters cubed. Okay, so we're looking at these errors for our apparatus. Now, for a burette, you do, as we've said, can measure to the 0.05 centimeters cubed. So each volume reading that you do or take is plus or minus 0.05. But because we always do an initial and a final reading, in other words, we take 2 readings, we need to multiply that. Error in a reading by 2. That is why you get plus or minus 0.10 here. So this accounts for the start and end readings. Okay, so 0.05 times 2, or 0.05 plus 0.05. Okay, so once you know the errors associated with each instrument that you're using, it allows you to work out the percentage uncertainty in any readings or measurements that you make. Okay, and to do this, it's a very simple calculation. The percentage uncertainty is simply the error, which is plus or minus whatever instrument we're looking at, so plus or minus 0.001 for your balance, and the measurement made on the apparatus. So if you weighed 5 grams, let's, for argument's sake, say you don't do it by subtraction, so you just look at the reading on the balance, then it would be 0.001 divided by 5 times 100 to get you the uncertainty. If it is weighed or obtained by subtraction, then you would need to multiply that by 2 because you've done a reading for the mass of your solid plus weighing boat, and then you've done a reading for the mass of the weighing boat on its own. So those are 2 readings, and so it will be 2 times the error associated, and then the bottom quantity will be obviously the difference in mass that you've just calculated. Okay, so that's the percentage uncertainty. And as an example, you can do the same for a burette. You've got 0.1 divided by the average titer times 100 to get the percentage uncertainty. And examiners like to ask students about how to reduce the percentage uncertainty associated with a practical. Okay, so for instance, if you wanted to reduce the uncertainty in the mass measurement, then you might want to sort of change this value here. So you might want to make that value smaller. In other words, the error associated with the balance, you might want to make that smaller, and so you might want to use a more accurate balance. So changing the instrument to use one that has a smaller error. So it might be a 4-figure balance, or 4 decimal place balance, which would be 0.0001 gram plus or minus. So you might want to change the apparatus, which would affect that top number there, the numerator. You might also decide, well, let's change or do something to affect this bottom measurement here. So if we were doing a titration and we wanted to reduce the percentage uncertainty for the burette, we might therefore choose to use a more concentrated solution in our conical flask, which would lead us to use a greater volume in our burette. So we would be wanting to increase the average titer significantly so that this term becomes a bit bigger, and so that we reduce the percentage uncertainty when we do that calculation. Okay, so these are things you need to think about, and it's fairly straightforward to think about it if you consider what will affect that term there and what will affect the bottom term there. So that term there is your choice of apparatus. So do you use a measuring cylinder versus a burette or a pipette, which have a much smaller error, whereas a measuring cylinder has a much larger error, or do you use a higher concentration of your analyte, the thing in your conical flask, so that you get a larger, tighter volume, which therefore increases that bottom term and again has the effect of reducing the percentage uncertainty. So these are the things you want to think about. Okay, and finally it says to calculate the maximum total percentage apparatus uncertainty. So all the different pieces of apparatus you've used to measure or take readings, you simply add up all the percentage uncertainties or percentage errors, and that gives you the overall uncertainty for the apparatus. Okay, so that is useful to know because you can then compare the overall uncertainty of all the apparatus with the percentage difference in your final answer versus the actual or expected answer. So if your for instance, if your titration is 99% accurate, because you're within sort of 1% of the actual answer, then you compare that to the total sort of percentage uncertainties, then you can sort of analyze your results sort of in that quantitative way. Okay, so let's look at this point. Let's look at some practice questions to do with the titration, the sort of titration that we've just seen. So let's have a look at this question from the 2017 AS paper. This is question 24. We're not going to look at this bit on redox. We want to move on to the part on titration. So a student plans to determine the concentration in moles per decimeters cube of ethanoic acid in a bottle of vinegar. The student will carry out a titration with aqueous barium hydroxide, and the student's method is outlined below. So the student takes a 10 centimeters cube of vinegar from the bottle and dilutes it with distilled water to make the solution up to 250 centimeters cube. So that's going to go into your volumetric flask. And then they add the diluted vinegar to the burette. Okay, so this time round, the standard solution is well, it's not quite the same experiment as we've just been describing. You have made up your unknown, so not your standard, I should say, it's quite the opposite. We don't know the concentration of the vinegar, but typically that would go, your vinegar would then be pipetted into your conical flask, but she's or he is doing it a different way by putting it into the opposite, by putting it into the burette. Again, no problem at all, that should work perfectly fine. So you've got your vinegar in your burette, and then you're going to use that to titrate your barium hydroxide, which we know the concentration of. So the barium hydroxide has a concentration of 0.45 moles per decimeter cubed, and we've got 25 centimeters cubed of it accurately measured using a pipette in our conical flask. Okay, so the mean titer, we're told, so the volume of your diluted vinegar that you're adding, the average mean titer is 25.45 centimeters cubed. We've got balanced equation for the reaction between barium hydroxide and ethanoic acid, and molar ratio, which is important, is 2 to 1 of ethanoic acid to barium hydroxide. We were asked to calculate the concentration in moles per decimeters cubed of ethanoic acid in the original bottle of vinegar, okay, and to show our working. So first thing we want to do is to make sure we've got the right data associated with the correct substance. Okay, so we've got vinegar, which is 10 centimeters cubed of vinegar from the bottle, and this is made up to 250, so it's diluted to 250, and we then are going to titrate 25 centimeters cubed volumes of barium hydroxide of concentration 0.045. Okay, so I know which numbers are to do with barium hydroxide, and I've been told that the mean titer of our diluted vinegar is 25.45. So all the yellows belong to vinegar, and the reds belong to our barium hydroxide. Okay, and then we need to make sure that we're aware of the molar ratio, which is 2 to 1. Okay, so the first thing I'd do is to calculate the number of moles of the substance. I've got enough information to calculate the number of moles for it. And this is, of course, barium hydroxide, because we've got a volume for it and we've got a concentration for it. Okay, so moles of barium hydroxide is going to be equal to the concentration, which is 0.045, times the volume, which is 25 centimeters cubed. Divide that by 1,000, and that would give you the volume in decimeters cubed. Okay, so 0.045 times 0.025 gives us 1.125 times 10 to the minus 3 moles. 1.125 times 10 to the minus 3 moles. Okay, so that's the first mark out of the way. Right, so what do we do with that? We need to look at the molar ratio. So the molar ratio we've seen already is 2 to 1, which means for every mole of barium hydroxide you've got, you're going to react it with 2 moles of your ethanoic acid in your vinegar. Okay, so we can work out the moles of ethanoic acid in our 25.45 titer volume. Okay, so that's very important to note that 25.45. Okay, so that would be this number here times 2. Okay, so that would be 2. Let's write it out in full first. 10 to the minus 3, multiply it by 2, which would give us 2.25 times 10 to the minus 3. Okay, so we now know the moles of our ethanoic acid in 25.45 centimeters cubed. What we now need to do is work backwards to see how many moles we've got in our volumetric flask of volume 250 centimeters cubed. Okay, so let's do that. So we've got 2.25 times 10 to the minus 3 is what you have in 25.45. Therefore, in 250 centimeters cubed, we're going to have 2.25 times 250 divided by 25.45. Okay, so if you do that, that gives us 22.1 sorry, we're looking at, so what we've just done is worked out how many moles we've got in our 250 centimeter cubed solution. Okay, so 22.1 moles. Now, if we want the concentration in our sort of original bottle of vinegar, remember the 250 centimeters cubed in our volumetric flask is the diluted version of our vinegar. So we've still got one more step to do. So we need to go back one step to the undiluted vinegar. So concentration of undiluted vinegar. So this 250 centimeters cubed is diluted. So concentration of undiluted vinegar is going to be the number of moles, 22.1. Now it is 22.1 because when you take the vinegar from the original bottle and then dilute it, you don't change the number of moles of your ethanoic acid present. All you're doing is adding a little water to change the concentration, but not the moles. Okay, so 22.1 divided by the original volume, which was 0.01 decimeters cubed, or 10 centimeters cubed over 1,000. 10 over 1,000. You want to write it that way. Okay, so 22.1 divided by 0.01. Now, you may well have spotted, no, I think we're good. So 22.1 divided by 0.01. Oh, where have I gone wrong? I have made an error somewhere. Let's work backwards to see what's going on in our calculation. So we've got 1.125 times 10 to the minus 3 moles of our barium hydroxide, which we then multiply by 2 because of the molar ratio there to give us 2.25 times 10 to the minus 3. Let's check that. 1.125 times 2 is equal to 2.25. Okay, so far so good. Okay, so now this is the number of moles in 25.45 centimeters cubed of vinegar. Okay, so we've got 25.45 and 2.25 times 10 to the minus 3. Therefore, in 250 centimeters cubed of our vinegar, you're going to have 250 times 2.25 divided by 25.5. Okay, so let's double check that. So 250 over 25.45 is equal to that. And if you multiply that by 2.25, that's where I've gone wrong. It should be 2.25 times 10 to the minus 3. 2.25 10 to the minus 3. That gives us 0.0221. So I was out by sort of 3 orders of magnitude because I was a bit sloppy with my standard form. So let's change that to 2.25 times 10 to the minus 3. And that, of course, then gives us 0.0221. 0.0221, and that therefore means we've got 0.0221 over 0.01. Okay, so that gives us a final answer of 2.21 moles per decimeters cubed. Okay, so this shows the importance of setting out your calculation very clearly so that when you get an answer at the end that doesn't quite make sense, you then want to, so instinctively I thought, hang on, you can't, that concentration of 2,210 so is way too high to the concentration of vinegar in a bottle. Going back and working through sort of line by line where the error might be, if you set your working out very neatly and accurately, then it's very easy to do that. Okay, so moving on to the final question. It says, suggest one assumption that the student has made that might mean that their calculated concentration of ethanoic acid in the vinegar is invalid. Now, the calculation we've just carried out would only be true if we're certain that vinegar is the only, or rather ethanoic acid is the only acid present. Okay, so the assumption is that ethanoic acid is the only acid present. Okay, so that is the assumption. It says, predict with a reason how the experimental result would differ from the actual concentration of ethanoic acid if the assumption were not correct. So if the assumption were not correct and there was another acid in there, then of course you're getting a concentration based on 2 different acids, and so the contribution of ethanoic acid to the number of moles and that volume is actually sort of less than you think. Okay, because you've got another acid present. So so the actual concentration would be less than you would think. Okay, so the concentration you've worked out isn't just down to ethanoic acid. There are other acids present, and so the real concentration of ethanoic acid is actually less than what you've just calculated. Okay, so that has been hopefully a good refresher on acid-based titrations. What I'd urge you to do is go away and sort of review the different sort of aspects of the technique required to obtain accurate titration results, and then to go one step further and tackle some actual titration calculations of the sort we've just looked at. Ones that require you to think about dilution factors, and ones that require you to think about sort of moles of solute in your solution, and what might happen if conditions aren't quite as they seem. For instance, if you've got other acids present, how would they affect your titration calculation? It's been a pleasure, as always, to join you on this Sunday afternoon looking at these questions. If there are any questions on titrations and acid-based titration specifically, do drop us a line that boosts revision, and we will be more than happy to get back to you with answers. Thank you very much for joining me. Look forward to seeing you again soon.